I'm going to go ahead and introduce Professor Cherie Kagan, who's going to tell us a little bit about the Internet of Things for Precision Agriculture Engineering Research Center. So I have a bio of Cherie. It's embarrassingly long, so I'm not going to read the full bio, but somehow she's simultaneously the Stephen J. Angelo Professor of Electrical Systems and Electrical and Systems Engineering at Penn. She's also Associate Dean for Research of the School of Engineering. She's Director of the NSF Engineering Research Center that she's about to tell you about. And then in her spare time, she's also President this year of the Materials Research Society. So we really are thrilled to have Cherie here to take a little time with us and tell us about this exciting engineering research center. So Cherie, let me turn it over to you.
Great, thank you, Mark. Can you see my slides and can you hear me okay?
I see a little picture of you, but I don't see your slides.
Ooh, I have to, sorry, let me see if I can get out of this to fix that. Sorry about that. I'm gonna try it, but I shared my screen. Let's see if I can figure out why.
Okay. We see you now instead of your photograph.
Oh, well, that's something. I'm going to try and share content one more time and see if that works. Everything on your screen, okay. Can you?
Back to your picture.
You don't see my slides.
We see the picture that you would see if, say, your video were off.
Let me see if I can fix why that's the case. Oh boy.
Does it make sense to maybe use your computer for the...
Yeah, I'm going to leave one on for audio and I'm going to switch the other. Give me 30 seconds and I will be back on top of this. Sorry about that. I had a little computer failure yesterday that I'm trying to recover from. All right, I should be there in just a second. And I'm going to turn off, I won't put audio on this one so that you can not listen to the sounds. All right, just about there. Click enough buttons. Great, can you see this now if I put it into screen share mode in just a second?
Yes, that looks great.
All right, great, thank you. I appreciate your patience. It's always not fun when a computer fails just before you're supposed to do the presentation. All right, and I'll hide enough things here, hopefully, to get them out of the way. Anyway, I want to just thank Mark and Pat and all of the organizers for the opportunity to introduce you today to the NSF Engineering Research Center for the Internet of Things for Precision Agriculture. And I just want to also say that I'm very informal. I'm very happy to hear people's questions and get you excited about this topic and the opportunity for sort of nanoscale IoT to make an impact. And in this case, I'll share with you a story where, you know, we really have a center that brings together 4 institutions that you can see here, from obviously Penn, Purdue, the University of California, Merced, and the University of Florida. And on behalf of my colleagues that we all work together to make up this center, we're happy to sort of share this story with you and tell you a story too, and the opportunity for this IoT for space to make an impact on sort of a societal grand challenge of food, energy, and water security. So that's really where we started in thinking about the opportunity that we have here. So I thought I would just start by introducing you buttons to as a center, of course, we have a vision, and we really looked at the sort of the challenge that we face in food, energy, and water security. And I'll just say that this is an area that's very well articulated by both the United Nations Food and Agricultural Organization, as well as the USDA. And they really frame the challenge in the idea that we really need, and I'll say the numbers up here vary a little bit on the report that you read, but they all call for sort of an increase in the production of food and a decrease in the use of energy, water, and agrochemicals in our farming practices. And that really is driven by a population that in the United States is anticipated to grow to 400 million people by 2050, but worldwide to 9.7 billion people. And so there are obviously more people who, and we need more food, but it's going to come not because of more arable land. That area is really largely fixed. There's a lot of competition for land. As you're all familiar, there are increased demands for our resources like water and energy. And we always worry about having sustainable practices, in particular, as you hear about the use of things like fertilizers and chemicals in farming that can also have sort of negative impacts, for example, on algae blooms and water supplies and things like that. So we looked at establishing our vision, which was to ensure food, energy, and water security. And then, of course, as scientists and engineers, we want to do that by advancing technology. So I thought that I would go in and just I'll skip along here and introduce you to our mission and start to tell you a little bit more. Of course, right ahead in our mission is this connection of developing Internet of Things or IoT technologies. And we really viewed that as an opportunity space, that as a way to make an impact and really look at the opportunity to influence precision agriculture. And also along with that, a part of our center, which I'll introduce you, is really an educational activity to really train a diverse workforce so that lots of people are involved. And I'll introduce you sort of to our partnerships as well with industry, government, and venture companies, for example, as a way to really build and bring together an entire community that really is required with lots of different expertise and interests as a way to challenge, to address this challenge through technology of food, energy, and water security. So I thought I would start with some of the motivation, and arguably this is our schematic, but to share with you a little bit about how agriculture is done today. It's mostly done still by what's known as crop scouting, the idea that manually a farmer or they hire a service to go out and sort of take samples from the field, which is very labor intensive and costly. And the challenge currently is that in some cases, there's limited to no technology available to address some of these problems in agriculture. So for example, sensor technologies, there are some. Sometimes they're they're very costly compared to, as I'll talk today about the opportunity space and really the ag specific problem of introducing technologies. So some of these sensors are limited or non-existent to really capture the, really spatially, temporally, and compositionally all the variables and the spatial and time scales that are important for us to really get a picture of what's going on in the field that influences the health of crops. Often there are some examples where data is collected, but often it's siloed in a piece of equipment. So for example, even if the tractor were to have some kind of data collection capability, it's often, in a little can, for example, in the tractor itself. And most farms are in rural areas. And so there's also a challenge in communications, that the infrastructure just isn't there to really support sort of a larger use of data currently. And then even as you look at, when there's an observation that a crop might not be healthy, often the interventions that are taken are often sort of reactive, right? It's already when things are, it's obvious, right, that the plant isn't healthy. And so you throw a lot of things at it. And that increases both the economic and environmental costs of farming. And so we really looked at the opportunity that, just for example, in the US, the crop production market is $140 billion per year business. And we want to be part of the solution to help to continue to support this. And one that interesting example here from a recent paper in Nature, Ecology, and Evolution just said, depending upon, just for pathogens and pests, I'll introduce you lots of variables that could influence the yield and resiliency of crops. But just pathogens and pests are estimated to reduce crop yield by somewhere in the range of 10 to 40%. And that range could depend on the crop, or even for the same crop on the region that it's grown in. But you can see that there's a lot of loss, and we'd like to prevent that loss in the system. So our way of thinking about this is to think about the opportunity for us to transform agriculture and sort of obviously make a picture here where the farm looks a lot busier, but to really think about building the farm of the future. And I think this really speaks a lot to today's topic on IoT and nano IoT in particular, as I'll try and share with you some of the ways that we think about introducing these technologies. But what you'll see is that the field, we look at the opportunity where we could introduce sensors everywhere, sort of above the soil surface, below the soil surface. Those sensors maybe need to be equipped with energy and communications technologies, where we really build these networks of sensors. And those sensors could either communicate with existing farming infrastructure or take advantage of the growing introduction, for example, of robotics, both aerial and ground-based robotics that are sort of emerging in the space of agriculture, so that we can again think about creating networks of some combination of existing farming infrastructure and robotics, and then to use those networks to be able to transmit the data and signals that you can't always see, or that you could get earlier by introducing sensors all the way through to the cloud, where we then have the opportunity to use and take advantage of the growing capabilities in data science using techniques such as machine learning and artificial intelligence as a way to really think about sort of bringing together all of this data and then providing a set of controls, for example, to the farmer to help the farmer make decisions that would help them improve outcomes in the field. And so we think about, really how do we as scientists and engineers come together so that we could sort of build integrated systems composed of all of these sensor communications and response technologies to think about capturing the microclimate at a much smaller length scale, and to do that with the right, appropriate temporal and compositional capabilities, so that we can understand the sort of stresses and ultimately improve the outcomes in the field. And we posited that the time was really right. The idea of precision agriculture has been around for 30 years, but we really think about, in particular, the opportunity for IoT, right? That now, that with the exponential growth in information technology and also in data science, and importantly, the idea that their costs are coming down, that we really have an opportunity now to impact agricultural practices. So I'll share with you a couple of motivational quotes in a moment, but it has been projected, for example, in a report by the USDA, that precision agriculture, I don't know whether that really encompassed all of the IoT capabilities, but it has the opportunity to increase, it was estimated to increase the value of just the US crop production market to $47 billion per year, which on $140 billion current bottom line, that would be pretty substantial. And so, not that we can do this alone, but we certainly hope as a center that we can be part of this solution. So I just thought I would share with you, as we sort of thought about this story and shared this story of what we wanted to do, just the opportunity for precision agriculture really being highlighted as a need in a number, both here in the United States as well as worldwide. One is in a report to the President of the United States by the USDA that was on a task force on agriculture and rural prosperity. And I just highlighted some of the key messages that, which really comes back to the first slide that I presented, that it's critical that productivity growth not rely on more cultivated land, water, or energy, but instead harness the power of innovation and technology. So as as scientists and engineers, we have to really like that, we really need to be part of the solution. And similarly, the World Bank Group on the Future of Food also wrote that as a key message that digital technologies have the potential to improve the efficiency, equity, nutrition and health, and sustainability in the food system. So as we think about both, here in the US as well as worldwide, to really be able to make an impact on society, we really think about the opportunity that we can do that through technology. So I thought now I'll sort of get you into a little bit, introducing you more to IoT for Ag as a center. So it's part of what's known as the Generation 4 of NSF Engineering Research Centers. So we're the part of the first class that just started last year in September of 2020. That's part of the Generation 4 class. So I'll just share with you a little bit about that center. Is that the center basically has an opportunity for 2 5-year timeframes for it to operate. After 5 years, we'll have to write a renewal proposal, but it's one where we is a center that has federal support in the amount of $26 million for the first 5 years, and something just a little bit less for the second 5 years. And we really look at the opportunity for us to come together as researchers and bring together a community and think about how best can we capitalize on this federal investment to really, realize the vision and mission that we set out, together in a sort of, and I'll explain what together means is, us in academia reaching out to industry, thinking about the end user, farmers, to have really everybody feel a part of this and guide this, the directions of the center. And then we already think about 10 years out of becoming, sort of self-sustaining, both in terms of our technological output, for example, our education and so on. So one thing about these Generation 4 engineering research centers, there are 4 pillars, and I'll try and just introduce you briefly to each of them. I'll try and talk a little bit more about the research to share with you some of the directions and really the connections to this area of nano IoT. So I'll talk about our what we call our convergent research, and then share with you briefly some about our workforce development, our diversity and inclusion, and also introduce you to our innovation ecosystem and how that really works with all of the pillars of the center, is an important part in guiding the directions of the center, so that all in all, the sort of direction and vision we have to impact society could be realized. So, well, I guess Mark had a very similar slide, so I'm not going to say very much other than I think I have one more bullet on of the 10 big ideas, which is NSF Includes, which I think you'll see as we think about bringing together a diverse community, in addition to the sort of research and opportunities that we have through these examples, building an infrastructure that means anywhere from the kinds of discussions that we have here through the NNCI to thinking about infrastructure for us also in some of our capabilities out in agricultural farms. So I'll just share with you this instead of reading through this list, and just to think about how many people can be involved already. This is a picture of all of our faculty, staff, students. Some are REU students, some are our advisory board members across 3 of the pillars, and I'll in a little bit later I'll introduce you to our innovation ecosystem. But I just want to say that activities like this really require a sort of institutional, disciplinary, and demographically diverse group of people to really come together and work together to make this possible. So we're very encouraging to have more students, more industry members, everybody come to join us to really help us to make this a success. So I thought that I'd start to drill down a little bit and tell you what convergence means to us. Something that we really worked hard to understand and to think about the opportunity that, to tackle a problem like the one that we set out, we really needed the right team. And what you'll see as I describe sort of how we work and the idea that we look at building systems, I'm going to tell you that we, from a standpoint of our research activities, we've, I'll try and relate that to the storyline of what we want to deliver on, but we have 3 thrusts within the center. One is on agricultural sensor systems, one is on communication and energy systems, one is on agricultural response systems. And it sort of takes all of these systems, I'll explain, back to our storyline that connects to really deliver on the integrated systems that we want to build. But it also takes bringing together a lot of different disciplinary expertise. So what I'll share with you is that, in agricultural sensor systems, right, we really need, right, you'll see a mix of folks, and obviously from different institutions, but that bring together plant and environmental science with, right, with faculty and appointments in agronomy and agricultural engineering and sort of agricultural economics and environmental science, with, what we think of with, our engineering disciplines that impact science, sensors, robotics, and being able to map the fields using cameras, for example, on those robots. Similarly, you'll see that we have expertise that brings together in Thrust 2, sort of the power of both the sensors and the robotic fleet, as well as I'll share with you sort of edge and backhaul communications, as Mark already alluded to the importance of communications and thinking about our technologies. And then finally, in agricultural response systems, where again, we bring together people from different disciplines and different expertise, again, all through our sort of ag and engineering disciplines, to really look at, bringing together machine learning and sensor fusion, but with a control where that we use these techniques as they're constrained by the problem in agriculture of making them sort of biophysically relevant, to make sure we ground the kinds of response systems that we develop. So it really brings together a very diverse team of experts to have this kind of dialogue. So I just wanted to share with you too that I said, well, we have 4 institutions, and this is a map to give you a sense of where different types of crops are grown across the United States. And you can see that the institutions that are part of this engineering research center exist where we have lots of activity in farming. And so you see that in the Northeast, the South, the Midwest, and the West. And it gives us also as a center an opportunity for us to think about how we create technologies, but that also speak to the diversity of crops and the different agricultural environments that we have in our across the United States, and is represented by our regions. So it gives us an opportunity to look at, the same kind of crop, but in different regions, to understand, for example, how our systems operate in those different regions. And then of course, to look at a diversity of crops, which you can see as just some of the sort of examples that are shown for each of the institutions. So in doing that, as we think about building these technologies, we want to bring them together to create these integrated systems. And as we think about the food supply chain and agriculture in the US and across the world, we kind of group these into thinking about developing systems for tree crops, as shown here, an example, and also an example of row crops. And just to give a sense too, is 3 of our institutions, Purdue, Merced, and UF, are land grant institutions. So something a little bit that this community may not be as familiar with is that as land grant institutions, they have what are known as extension facilities, where these in fact are just 2 examples of photographs from fields at these extension facilities, where there are sort of control facilities, plot scale, even farm scale facilities, where we can take our technologies and bring them and test them out in these environments as a way to sort of ground our research, but also as an opportunity educationally, where agricultural professionals and students can come and work in these spaces, and we can also use it as a conduit to translate our technologies out to the community. So I thought, well, one thing that is sort of a pillar of engineering research centers is something called the 3-plane chart. So we, of course, have a 3-plane chart. And what it really says is that as we look at this as a problem where we have to really integrate all of these different systems and technologies together, which I described in sort of the pillars of our 3 thrusts, they really all span sort of developing fundamental knowledge that is important for us to build technologies and then ultimately to bring them together. And while this is a busy slide for each of the thrusts to really try and represent all of the aspects of science and engineering that we work in, I just thought I would give one example. And I thought I would give an example here in thinking about, what's special, what's the challenges that we have to address, so that, we think about the fundamental knowledge as we try and push and, for example, and think about the limits of electromagnetics. In particular, as we think about how do we, if we want to get signals from below the soil surface, how can we get those signals out from below the soil surface and then develop those kinds of communication technologies so that we can get the data from this below the soil surface, above the soil surface, out to those kinds of networks, do it in a way that's reliable and not stolen by others, and ultimately communicate that to the cloud. So it really shows this kind of connection that we have sort of vertically, for example, within the thrust to understand, and for example, in thrust 2, between understanding the challenges of electromagnetics to developing edge and communication technologies. And then it also brings together all of the thrust. So it's also horizontally integrates the center, whereas, you know, these sensors, for example, are being built largely in thrust 1. Thrust 2 has all of the energy and communications challenges I've described, but getting the data out, right, is what's needed as an input for thrust 3. So as Mark likes to say, who is a leader co-lead of thrust 2, is they're really essential right in the middle in thrust 2 to develop those communications capabilities. So I wanted to now take this picture that I showed you before of all of these sensors, communications, and response systems. And as we overlay this with our thrust and sort of tell the research story, we think about it as, so I, as an electrical engineer, think of this as a wiring diagram to think about how do we map all of the work and storyline we need to build these integrated systems into the work that we'll do in our thrusts. Our colleagues in agriculture were perfectly happy with this diagram as long as we were also willing to call it a flow diagram. But it's an example where we look at, you know, in the field where we have to look at, we want to embed sensor technologies below and above the soil surface to really understand variables that are here, to equip that with energy and communication technologies to enable as needed those sensor technologies, to develop, to communicate that data at the edge to existing farming infrastructure and robotics. And those robots, as you know, also need communications and energy technologies for those to operate, especially at the scale of agricultural fields, to then have some data analysis on board and then to communicate that and backhaul communications where our team working in data science can then act on that data and develop controls to help and assist the farmer with a set of recommendations to come full circle so that they can act in the field. So I just want to make sure I'm doing okay on time. I just thought I would share with you some of the sort of, as we look at the kind of breakthrough technologies that we want to develop in IoT for ag. And also just as we think about IoT, it's not all of IoT, but we think about what are the agricultural specific use cases that we have. And the reason I say that is that agriculture presents a sort of different set of challenges, right? A different challenge of scale, where, you know, compared to some of the, right, if you think about an agricultural field in comparison to IoT, for example, that might be used in medicine or for health within the body, right? So we have very big scales. They operate in very different environments that are often uncontrolled and unstructured. And it's also very much driven by some of the socioeconomic challenges of meeting the needs to make it affordable and accessible for the end user farming community to use. So I'll just share with you as we look at each of these thrusts that we think about our technologies looking at multi-mode, low-cost, distributable, environmental, and soil sensors. And so you can see some of the examples here of things that look more conventional, of sensors being introduced in trees. These are some sensors that very much at the heart of requiring a lot of fabrication and a lot of time in working in fabrication facilities to develop, as you can see here, this is a colorimetric sensor that we're putting on leaves that change color, right, in response, and are built on, you know, a lot of capabilities in sort of low cost, large area fabrication, but of making, you know, very small nanoscale sort of sub-wavelength features that are very important. We also have technologies in autonomous ground and aerial robots, as you can see here, that can be deployed out into agricultural fields to see, for example, the bottoms of the plants, to operate, in very difficult and unstructured environments. In thrust 2, in energy storage and delivery technology that can happen at field scales. And also an important part is, as we introduce these technologies to develop material systems as part of the environment challenge, is ones also that are often, that have to be biodegradable and biocompatible. And so this is an example of some battery technologies that Mark Allen's been developing for introducing small amounts of power in sensors that could operate below the soil surface, but have to be biodegradable, right? To be, if we really deploy these sensors in large quantities, we're not going to go back and pick them up. So they really have to meet the environmental need. We look at, as I mentioned, the agricultural specific challenge of edge and backhaul communications, where there's often very little communication technologies at large scale in the rural environments. And so it's not the same, it's very different than operating on thinking about, 5G technologies, right? So how do we do that backhaul? And how do we get signals and communicate, as is shown here, how do we get communication and in places where we can get signals out from below the soil surface? And finally, in thrust 3, the technology we're looking at are creating biophysically constrained data-driven models for field analytics. So for example, how do you take all of this data that may come from different sensor systems, for example, an overlay where you could use sensors that we're developing here, but for many different variables, ones that could also come directly by imaging from camera suites, for example, on robotics, to even overlaying that with available satellite data or weather data. And how do you overlay all of that data to be able to create sort of that full picture? And ultimately, how do you take that picture and create a decision ag interface? For example, something that might look like this, where a farmer would then know and say, oh, I should go here. Here's a hotspot where I could make improve, if I take some intervention, I could improve the outcome in that field. So I'm just looking at the time to make sure and see how I'm doing. I think maybe I want to try it. I won't go through all of these. Just to look at the problems of all of the variables. I'll go through these quickly. But all of the variables that we have in our fields that are a challenge for us to be able to get data out that all impact the health. And it's also, by the way, these technologies also come back full circle to scientific questions, where our agronomists really don't, they don't have the data with the spatial and temporal capabilities, or for all of these variables to really develop models of how they impact crop yield and resilience. And so we both want to understand how to deploy these technologies, but also how do we use these technologies as inputs to understand our science. So because of time, and I'll let Mark chime in, or Pat chime in, I think I wanted to leave time for questions. So I'm going to skip through. I tried to speak fairly quickly, and I apologize for doing this. I'd love to share more about all of the work that we're doing. And just tell you that, this is also something that we look at how we can, use both to excite, this connecting our science and technology to the opportunity to excite, all sorts of communities about science and engineering, particularly at the pre-college, community college level, but also to excite and grow a community of new agricultural professionals by introducing technologies into that workforce. And then also to go all the way through to, get our science and engineering workforce, often trained at universities, to get them excited by making an impact on society. So we really like this kind of mix. And then finally, the opportunity to educate professionals through our extension facilities and partnerships to be able to train them in how to use how to use technologies to ultimately in the fields. So I won't go through. We have a large community. We try and bring all of these groups together and really look at all of the aspects from sensors and communications and energy to response systems that we try and educate. That we bring this diverse group together to educate one another. And so you can just see some of the examples of what our students have been up to and learning, as well as our faculty as we train each other. And we try and bring together a very diverse group and realize to show them the opportunities that there is through the excitement of the center. So we have programs to try and recruit students, often, from, to broaden the participation of underrepresented minorities, for example, and women in these activities. So we just held a workshop to try and encourage and mentor students to help them through, for example, the PhD program and to look for fellowships. We have our own culture within the center to really, feel that people are included and connect to the leadership of the center, and even to ask questions about. We had watched a movie called Coded Bias, which I thought was very interesting for us to really develop an awareness of how, as we build these IoT technologies, how the design mostly about algorithms, but how do we make sure it's accessible to a diverse group, which is our end user, actually, is a very diverse representation. And finally, I wanted to introduce you briefly to the innovation ecosystem. And so for our innovation ecosystem, we think about what's called an industrial practitioner advisory board, but really the opportunity where industry, government, venture, and innovation partners, as well as we created something called an ag systems advisory board, end users of growers and ag professionals, but really to bring them in as part of the center to help us guide the projects that we set out to do, and to really help to create new directions, but ones that, to make sure that our technologies really reach out to the stakeholder community and will ultimately make an impact. So we welcome people to join, and so we're excited to also share more about our industry membership program. And I'll just say currently we have 18 members that really map onto the kind of technology spaces that we have, from the sort of physical systems and sensors and robotics to the cyber systems and the data side, to really looking at folks who are, large companies that integrate them all, along with institutions that will help us transition and understand the regulations that are important in our environments, and actually the end users of all of these technologies who come together to help guide the direction and be involved in the center. And so we continue to onboard new members and welcome anyone who might be interested, to please reach out. We're very happy to have and sort of grow this community who is interested in the IoT space, for the example of precision agriculture. So with that, I'll just sort of say what we hope to do over the next 10 years and beyond, when we continue to be sustainable, is to develop these integrated sensor communication and response systems to enable this farm of the future through our science and engineering, to really build a workforce that's educated and can both build and act upon the technologies that we develop. And a few corny statements, but we like to think that we could help to realize more crop for every drop of water or joule of energy, and to develop sustainable practices, so that ultimately, as a center, we deliver the people as well as the Internet of Things that will enable a food, energy, and water secure future. So maybe I'll stop there and be happy to take any questions.
Well, thank you very much, Cherie, for that presentation. I think you did a great job capturing the scale, both intellectual and physical, of trying to instrument the farm of the future. I see in the chat and the Q&A that there's a little bit of issues associated with collating questions in the Q&A. But let me ask one question that came in the chat. As we think about climate change and sort of think about the future of farming as how we can improve things today, how do you see the Nano Internet of Things help us there, perhaps keeping currently arable land arable, opening up new lands which become more hospitable, closing down old areas? How can our research in this center help guide farmers through climate change?
Yeah, thanks, Mark. Yeah, so this is one that we really thought of, and I mean, perhaps I should better articulate in that first slide. One we articulated in words, which is this challenge of food, energy, and water security is sort of, even more challenged by our challenges of climate change as the question asks. And so we really think that, as you look at the opportunity in IoT to, look at, obviously, the amount of land, we certainly don't want to lose the land so that it's not arable. So it's very important that we have and develop practices that, sustain the lands that we have. There are a lot of pressures on land use in terms of what's arable. People like to build things on it too, right? So even if the amount of land doesn't increase, we want to protect the lands that are arable and can be used for farming. And I think that coming to that question about climate change, we really do want to, we look at the challenge that, agriculture is one of the largest use of water. In fact, it uses 70% of available water. So it's a pretty big challenge. And then energy is one of the largest costs on the farm. And if you think about that, all of the potential impacts, if we, don't smarten up the field, right, that, all of those can contribute to the climate change problem. And so really, of course, we need food as people, right? But we do want to look to do that and to really think about how do we carefully manage our resources, land, energy, water, and then to do no harm, to limit any kind of harm that we might have in our practices, so that we help to farming to reduce their impact on climate change.
And I'm going to paraphrase a second question that came in from the chat. Do you see the nano-enabled Internet of Things being able to monitor what I will call second-order effects that could affect agriculture, such as, say, the density of pollinators or other effects that, rather than look just at the plants, I guess I would say, is there an opportunity to look more broadly at the environment using?
Yes, there certainly is. In fact, we think about the sensors as being, environmental or kind of plant being, on the plant or in the soil kind of sensors. And I think we can, the one thing that we look at is in the kinds of technologies that we're building in sensors, whether above the soil surface or below the soil surface, are ones where we have platforms, that those platforms then with the right kinds of materials that are, selective to different targets of interest, then could be used, and we could divide up the electromagnetic spectrum, whether at optical frequencies or radio frequencies, as a way to really get information about many, many variables. So this idea of multi-mode, right? The idea we could have, be able to sort of really broaden our perspective. And so on what we could sense and what we could collect. Obviously, we start someplace, but I do think over time, we've started to look at, how do we build sensors, for example, obviously, water, temperature, pressure below the soil surface, but we started to think about how do we design one specific for things like aflatoxin, right? And you can continue to, upon that sort of base of technology, think about expanding the sort of, the ultimate vision to think about, sort of different buckets of sensors that would be able to collect data and get those signals that we don't see by eye, but get those signals out and make those sort of visible to us, so that we could build and broaden the range of what we think of as compositions that we could measure.
Great. Well, thank you again, Cherie, for an inspiring talk as to where these technologies might go. And I can comment as a sensor guy. One of the things that I've really come to appreciate in looking at this problem is the importance of communications, right? So it's not just the sensors, but getting the information, collating it, getting it to where it needs to be. And so I think this truly is a nano-enabled Internet of Things problem that is being tackled in this center. So perfect subject for us. Really appreciate it. And thanks again for participating.
Thanks, Mark. Thanks, Pat. Appreciate it.